Yeah, so I was asking you guys which day are your free days because there is a chance for me to arrange the public talk, but I also need to confirm with the speaker as well. So remember the other day I was telling you guys that whether you're interested in hearing a talk about string theory, because one of my colleagues in my previous university, he d- he his research area is in string theory. So and he is a very interesting and very entertaining speaker. So every time he gives a public talk, he is quite popular, and so all the every time, yeah, so usually the general public will be very interested in his talks, and also he's also like willing to stay around and give the talk, and usually after the talk he can like stay behind and answer many questions and things like that. So let me try to arrange the things with him, but in and also I have also given you these questions on about which topics you like, right? Seems like yeah, so you guys, but most of you guys are looks like interested in hearing about string theory, but I think cosmology is the most popular topic among you guys, so that's interesting. I have some cosmology friends as well. I see whether I can get any of them to interact with you guys. Condensed matter physics very mixed. I guess it's understandable, but condensed matter physics, I think I should be more precise. There is condensed matter physics is actually a very big field. So the part that I'm more familiar with is condensed matter physics in the theoretical sense, and the reason is because the mathematics of condensed matter physics seems to be very similar to quantum field theory and also gravity, and because of this, some of theoretical physics works can be applied to condensed matter physics as well. So you heard about the holographic principle and things like that. That is partially related to this, and also so this is my job, right? So a lot of people are interested in this as well. So so we shall see lah. So at least I get an idea of which topics to emphasize on, and also yeah, maybe in the future we can sort of help you guys find a appropriate final year project in a topic that you guys are interested in. So the two suggestions here, I believe both of them is something about particle physics, right? So yeah, a lot of you guys are interested in particle physics as well, but ultimately I guess it's kind of obvious. Most of the different fields are kind of have some interrelation to each other. String theory is related to particle physics, and black holes is related to string theory, and sometimes cosmology as well. So it's not yeah, so I wrote the different categories, uh, but they can be kind of related to each other as well. Oh yeah, there's one category I haven't mentioned yet over there, but some of you are also interested in quantum information and quantum computation. I also have a lot of friends working in that field as well, because when I was a student in Singapore, there is a big center for quantum technologies in that university. So there's a lot of like research activities going on there, and this is where you hear things about like quantum teleportation, quantum encryption, like decoding encryptions, RSA factorization, all those kind of things, right? So most of it are pretty cool stuff, and yeah, so there's a lot of things, there's a lot of research areas going on as well. Okay, so yeah, so hopefully this will give you guys an idea of what the variety of physics is about, because I'm sure, like I know when students join physics for the first time, usually we don't really know what is going on, right? What does it mean to work in physics? And actually physics is a very broad field, so that is one of the different categories. Even when we listen to main campus talks, right? Yeah, so our main campus is like generally leaning towards one side of research area, which is, you guys always commented, is something about solid state physics and condensed matter physics kind of things, right? We have also biophysics and all different things. So it is actually not a one single field, Like someone from biophysics know a lot of stuff which I know nothing about, and then biophysics people know nothing about the things that I do. So in any case, let us continue on the topics. We will be discussing about the solenoids. Black hole related to quantum physics. Yeah, something like correct. Yes, that's our job, right? we physics is about solving unknown problems. How is black hole related to quantum physics? Yes, quantum gravity for one thing, and another thing is like the Hawking radiation. So Hawking radiation, you don't need quantum gravity, but if you combine the effects of black holes, and then if you calculate the quantum mechanics near the horizon of a black hole, you get Hawking radiation. So that is another way that is related. Okay, so lots of interesting stuff, right? And so yeah, another reason why I keep showing you guys this is sometimes what we are doing here is very tedious and very boring, but you know, we are sort of building up our foundation so that we can really go to solve the unknown problems. So let us continue on with the topic of sources of magnetic fields. We have learned how to use the Biot-Savart's law and Ampere's law already, right? So we're gonna use Ampere's law to derive the magnetic field inside the solenoid. So we have actually done this on Monday, but we were pretty rushed. So let me do this in more detail and more carefully, because solenoid is going to be important over the next few chapters. I guess the first thing I kind of rushed through is to explain why the magnetic field is zero approximately. So it's not exactly zero, but it's approximately zero outside the solenoid. And the reason is very simple, because if you look at the solenoid, right, the wire is coiled, and then the current is flowing here and then coming out and then coming down, coming out and coming down. So if I look at the side view, right, the wire is coming out on the top, so coming up on the top, and then go around and come down at the bottom, so going down at the bottom. So if I just take one coil, what is the magnetic field? We use the right hand rule, am I right? So let me say this is the part 1, this is part 2. So the wire, if I use my right hand rule, I can figure out the direction of the magnetic field created by this wire. I have shown you how to do this on Monday, right? You use your right hand, you grab the wire, this is the current, and then your finger is the direction of the magnetic field. So what is the magnetic field created by wire 1? So magnetic field created by wire 1, the current is coming here, so my finger is over here, so that means my magnetic field is in this direction. And then if I follow, it's in circle, so on this side my magnetic field is in this direction, right? So using the right hand rule. Now we look at wire 2. So for wire 2, did I remember to press record? I did, right? Yes, I did. The big diagram, current wrong direction. Which big diagram? You mean here? The left side. Oh yeah, the way I draw it. Actually, you're right. The way I draw it is in the wrong direction. Because I should be drawing it like this, right? I want to do it this way. So it's in 3D. So it's in 3D. I think it doesn't matter because it's the perspective, right? So the way I draw it is like, yeah, the current, you're coiling your string like this, so it's not so like this, okay? So then if you grab the wire, then the right hand rule is this. So it's not the wrong direction. I think it is a matter of perspective. So this the direction is correct if this wire is behind, right? This is a flat picture, so this is behind. And then if you coil it in and then you come to the front, so this is in the front, right? So you coil, and then you come down. Make sense? Right? Yeah. Yeah. So I know what you mean, but I guess it's understandable. So Yeah, so the direction is correct, but the main point is, yeah, you get some, it's one or the other. Okay, so the magnetic field created by wire 1 is this, and then wire 2. Okay, wire 2, use your right hand, your thumb goes into the page, and then the magnetic field created by wire 2 is this, but then created by wire 2 is this. Okay, and then now we see what happens on this side. So the magnetic field created by wire 2 is on this side, so here also is still this side, right? Okay, so I should use blue color for wire 2 and this. So this two is against each other outside the solenoid, and then the same story happens here. What is the magnetic field created by wire 1 on this side? So if I use my right hand rule, the magnetic field created by wire 1 is something like this side. So these two also against each other. Okay, and we shouldn't say it exactly cancel each other because the distances are different. So this B2 is more further away from the B1, so the B1 magnetic field is slightly stronger, so it reduces the effect, but it's not exactly zero. So I would just say it's approximately zero, but in any case, if the solenoid is thin enough, then the magnetic field outside is very, very weak, then it's approximately zero. But in between these two, right, in between these two, we see that these two are enforcing each other, they are supplementing each other, so the magnetic field is stronger in the middle. Okay, so that is the magnetic field inside the solenoid, and why it is zero outside the solenoid and non-zero inside the solenoid. So for solenoid, let me just write this. Magnetic field approximately zero outside the solenoid and approximately uniform inside. Okay, so this is our assumption that we will take for solenoid. It's not exact, but it's most of the time it's accurate enough that we can use it to do experiments and do calculations. Okay, so now we shall use Ampere's law to derive the magnetic field inside the solenoid. So let us say that the length of the solenoid is L, and then the total coils is big N. So from these two, we can calculate the number of turns per length, which is a quantity that we will normally define as little n. So it's just the total coils divided by the total length, right? Because it's going to be quite long, so the solenoid is approximately quite very, very long. So what we do is how many turns in a short length of a wire. So this is another quantity that we will use to solve, right? So the actual number of coils within a length L is going to be n times the actual length. Okay, so yeah, so I'm going to use the Ampere's law now. So does anyone have any question? Perspective drawing. Yeah, exactly, correct. Yes, but of course, don't worry, right? Issues like this, it shouldn't really it's not a big deal in the exam, because this is a physics exam. This is not an art. This is not an art course. So let's use Ampere's law to find the magnetic field inside. So I will take a small section of this, and let me draw all the wires. So not all the wires, but all the wires here. Okay, so let's take this section and then this section here. So I just take a small portion, right? It goes on forever, but I just need this part only. And then what I will do is Ampere's loop. Ampere's loop is a square of sides A. Okay, so I will take the ampere loop, which is the square of side A, so I will take this direction. Okay, so as I said just now, right, inside here my magnetic field is approximately uniform. Inside here my magnetic field is approximately 0. Okay, and the magnetic field is perpendicular to these two pieces over here. So what we can do is, yeah, we will find the loops in the 4 sides. So 1, 2, 3, and then the 4 sides. So let us use our Ampere's law here. So in order to use Ampere law, we need to know what is the enclosed current. Am I right? So what is the current enclosed here? So for each of the wire is having a current I, and then I just need to know how many loops are inside this enclosed current. So my enclosed current should be I times the number of turns in the square, in the loop, in the Ampere loop. Okay, and what is the number of turns of this Ampere loop? So it is the n times A. Am I right? Because the little n is the turns per length. So I times the length of A, I will get the number of turns. So the current enclosed inside the square is just I n A. Okay, so this is my current. So now we shall use Ampere's law. So Ampere's law is to say that the integral of B dl is equals to enclosed current times mu 0. So enclosed like this. And then B dl is a line integral of 4 sections. So I can split this into 4 pieces. This is the line integral of similar to the kinds of stuff that you would do in calculus 2, but we are doing a simple version here. So this is integral B dl of section 1 plus integral B dl, remember the vector of section 2, and then section 3 and section 4. And then my current enclosed is INA, so mu INA. Okay, so I guess it's pretty clear where this is going now. In section 1, B equals to 0. So this term is gone. In section 2, this is perpendicular. Section 4 also perpendicular. So this term is 0, 0, and then also 0. And then this term, the B and the L is parallel. So B dl is just B integral B dl, and it's just B times L. Okay, so this is mu I n A. So this is just the magnetic field times the A. So I got B mu I n A. And then I cancel this. So finally we got the magnetic field inside the solenoid. The common formula, I think some of you may have seen this in your high school before. It is the formula of mu n I. Right? So this is the magnetic field inside a solenoid. Okay, so this is the magnitude, but the direction, I guess, is pretty clear already, is towards the right. Okay, any questions so far? Okay, so that is how you find the magnetic field of a solenoid. This is a straight solenoid. So as I said, it will be important in several situations in the future chapters. Okay, then the next thing that we want to find, the first term, how, oh, you mean section 1, is it? Yeah, the first term is 0 because the magnetic field outside the solenoid is 0. Yeah, so is B is 0 outside the solenoid. And then the second and fourth term, right, here is 0, and then down here is perpendicular, so in either way is 0. So that is why these two are 0. The only non-zero term is this section here. So section 3, and this line is parallel to the magnetic field, therefore it is BL, B times A. So I'm integrating from 0 to A. Okay. And it's approximately uniform, so we take B as a constant. a cancel out result. It, well, we're not really using superposition. I don't know what you mean by superposition, but in this context, superposition means magnetic field 1 plus magnetic field 2 is B1 plus B2, right? But right now we only have one magnetic field, so that is, oh yeah, I guess B1 plus B2 out here is approximately 0. Yeah, I guess this is what you mean, right? And also here is approximately 0. And this one will add up, and this will help us calculate the magnetic field. Correct. Yeah, so remember the capacitor? Yeah, correct. So capacitor, the same story happened, right? Capacitor, the two plates. So in between the two plates, the superposition will add up the effect. But outside the plates, they cancel each other out. So same story. So the next thing that I want to show you is is called example 6.3.4 in the notes, but basically it is a toroidal solenoid. Okay, so basically I take a solenoid and then I just roll up in a circle. So this is what we want to do. So toroidal solenoid. So a solenoid that is in a round shape. So in the lecture notes we got a nicer looking picture over here. So this is the straight wire solenoid. So toroidal solenoid, basically it looks like this. Let me open. Pop up. Yeah. So I have a toroidal solenoid. Is basically torus or toroidal means donut shape. So it shapes like a donut, and then it wounds with total n turns of a wire, and the wire is carrying current I. So you can see this is another 3D perspective picture again. And then, but the way we draw it is let the outside wire coming out and the inside wire going in, right? So it's curling around, and then we just want to find the magnetic fields of the toroidal solenoid. So for the same reason as the straight line solenoid, the magnetic field is going to be 0 outside and then non-zero inside. So same reason. So should I write this here? Yeah, that's right. So for the same reason as the straight solenoid, the magnetic field is approximately 0 outside, but it will not be uniform inside the solenoid. Okay, so this is the difference between the straight and the toroidal solenoid. So it will not be uniform inside. Okay, so that is the key point here. So let me draw this right hand side diagram on this picture. In the lecture note obviously it looks very nice, so but let me try my best to draw it here. So inside is going into the page, right? And then outside is something like this. So the total number of coils is n turns. Okay, and then I will draw an ampere loop to be. So what's the direction of the magnetic field? Let us practice using the right hand rule. So the right hand rule, let's take this wire, right? What's the magnetic field created by this wire? So right hand rule, and then it's coming into here. So the magnetic field is this direction. And then same thing here. So if you use the right hand rule down, right, and then the magnetic field is also supporting it in this direction. So what I'm going to do is I will take, since it is pointing here, and we expect, of course, every point of the wire will do the same thing. So therefore my magnetic field will be going in circles inside the torus. So I shall draw my ampere loop to be a circle of radius r in this direction. So the radius of this circle is r. Okay, so I choose my ampere loop, circle of radius r inside the torus. Okay, so that is what we have for the ampere loop. So once I draw the ampere loop, I can now figure out what is my enclosed current. So the enclosed current is, remember, it's same like Gaussian surface. You just need to see what is enclosed by the loop. So the stuff outside, you don't need to care. So the stuff that you enclose is this, all the wire going inside. And it is totally the number of n turns. Each turn has carrying a current I. So it's just, the enclosed current is just n times I. Right? So each wire is having current of magnitude I. Therefore, n times I. So now we can use the ampere loop. So ampere law. So Ampere's law says that the integral of B dot dl is equal to mu I enclosed, right? And then if I take a small section dl, the dl is going to be parallel to the magnetic field everywhere. So B is tangent to ampere loop everywhere. So that my B dl is just the integral of B times dl. It's just B dl cosine 90 tangent, right? Cosine 0. So then the current enclosed is just mu ni. And then B is also for, we also say that, of course, yeah, for the fixed distance, the strength of the magnetic field is constant. So it's just B times the length of the circle. So it's 2 pi r. So I got mu ni. Therefore, my magnetic field inside the toroidal solenoid is mu ni over 2 pi r. So as you can see, this is the magnitude of my magnetic field inside the toroidal solenoid. So why is it not uniform? Because it depends on r, right? So B depends on r. So that's why we say it's not uniform. Okay, so that is how. Then of course, Ampere's law, just like Gauss' law, the final result gives you the magnitude, but the direction is you figure it out separately, which we just did using the right hand rule. Okay, like the magnetic field is this way. Yeah, so that was the magnetic field inside the solenoid. Oh, interesting question. But firstly, for this question, I think actually like most electrical devices uses a toroidal solenoid. Like yeah. So remember I was telling you about my handphone charger exploding, right? Yeah. So when it explode, I look inside and then I see like one of the pieces. It looks something like this. So so it's probably a solenoid, but for whatever reason, I think it serves as an inductor. The application of the toroidal solenoid or the straight solenoid is going to be inductor, and you can find it in many different components. So I think if you open your computer inside the motherboard things, you will see this type of things here and there, right? And most of them are circular shape, and these are, we will learn in the next chapter. For electrical circuits, this will work as inductors. Okay, so yeah, it's found in handphone chargers. It's found in computers. I'm sure there's many other places you can find this. But for like other natural phenomena, for inductors, let me think. I believe, yeah. So the nuclear cold fusion reactor kind of things, they probably use toroidal solenoid, right? So but I should look it up before I say because I can't remember now. Or the wireless charging, I'm not sure because I'm not familiar with this. It's possible like something related to induction. So using induction to do wireless charging. Why circular? the main reason is to fit inside your charger, to fit inside, because if you do a straight line, it's very bulky, right? Very like take up space if it's a straight line. So if you just coil it up and then it's in a circle, so you can just fit it inside your computer more easily. So it's just a practical reason. Particle acceleration. For toroidal solenoid in general is not used for particle acceleration, because it's just the magnetic field going in circles. And I have shown you just now, right, the video of the lab. Mainly it is more useful to have a uniform electric field, a magnetic field to control your particle beam accelerations. So that is one of the many different applications of the toroidals, of the solenoids, right, whether it's toroidal or otherwise. So you see, right, a ring again. So every time when we solve something in electromagnetism, we do straight line and then we do a circle, and then a straight line and then a circle, because those are the most symmetrical shapes we are capable of solving. And if you do more and more complicated shapes, the calculation become more and more complicated. Sometimes you can't even perform the integration. You need to use numerical programming to solve this. Actually, with that, we have finished chapter 6. So solenoid is the one like major application of how magnetic fields are created. So what we will go to is the next chapter, which is chapter 7. So chapter 7 is a big chapter because it involves theoretical stuff and application stuff. So I don't know how long we will spend on this chapter, but let's see. Okay, but it is a natural progression of what we have been discussing so far. So anyone have any questions so far? So the accelerator is what we have been discussing in which chapter? 2 weeks ago, right? I think one of the classes before the exam. Remember the day I show you the video of the lab? Yeah, and then we see how the particles going in circles. So that it is a uniform magnetic field in the vertical direction, right? Either going up or going down. So that is how it's used for the particle accelerations. Okay, so the next thing is called electromagnetic induction. A more fancy term now is what we call the electrodynamics. So what is electromagnetic induction about? I guess a starting point is just let us revisit what we have learned so far. So so that to put everything in context. So what we learned so far is the following, right? We look at charges, and we have learned, thanks to Coulomb's law and Gauss' law, charge creates an electric field, right? So you have a charge, and then you have electric field created all around it, right? And this is where I keep emphasizing that we are talking about the electrostatics. Okay, and this is where where we get electrostatic. So our assumption here is the electric field is constant in time. So therefore, if it's constant in time, we can take this assumption and say that the electric field is 0 inside a static conductor, right? And then for uniform conductor, you do all this calculation. We have done this from chapter 1 to 4. Then after that, we talk about current. So current is basically moving charges, right? dq dt. So a charges that is flowing, and this creates a magnetic field. And here is we did not use this term quite often, but it's kind of obvious. Is we should call it magnetostatics. and we have been solving the situation where the electric and magnetic field is constant in time, right? So over here we use the Coulomb's law, Gauss law, and then over here we use Biot-Savart's law, and then Ampere's law. Okay, so in this method we have focusing on the case where magnetic field is constant, electric field is constant. Okay, so this is just like yeah, I'm just repeating what we have spending all the time been doing so far, right? So what is our next step? So this is the following, right? So one observation, one hint of what is about to come next is like is the following. Moving charge created magnetic field. Moving charge, right? So charge created electric field, and then this charge is moving, it will create a electric field. So does this mean this has something to do with a changing electric field, right? A moving charge that is moving, so a changing if I have a charge that is not moving, then electric field is static. Okay, but if the charge is flowing, if the charge is flowing, then the electric field will also follow, right? Then this is a changing electric field. The electric field is not the same over time. So this is a changing electric field, but moving charge also means current. And then this current created a magnetic field. So the first suspicion that we start to have is that a field that is electric field that is non-constant in time will create a magnetic field. Okay, so that is our first suspicion. Then this is what we will learn in this chapter. So this chapter we have learned other ways to create a electric and magnetic field, which is to say that a changing electric field creates magnetic field, and at the same time a changing magnetic field creates an electric field. So this is other ways to create electric field and magnetic field is the following. Changing electric field, it will create the magnetic field, and then changing magnetic field creates an electric field. Okay, so we can also start to see already. I have mentioned something about Maxwell's equation at the beginning, right? Maxwell's equation is the set of 4 equations that determines almost everything about electromagnetism, and we can kind of see that already. We have 4 things here, 1, 2, 3, 4. We have learned the first 2 phenomena already. What we will do in this chapter starting today is to learn the next 2, right? But there are some issues that we need to settle. Once we have figured out all these issues already, then we have a fundamental equation for each of these phenomena, and then we can have the 4 Maxwell's equation, right? So one of the goals of this chapter is to derive Maxwell's equation, and this is one of the things that if you're a theoretical physicist is something you will like a lot, because theoretical physicists is we want to condense all our knowledge into a few sets of assumptions and equations, and from there we can derive all the results. Okay, so yeah, mathematicians and theoretical physicists is something that they want to do all the time. Okay, so that is our main objective of this chapter, and once we have learned how this happens already, then we start to apply them to different problems like the circuits, you know, LRC circuits, this kind of things, because for LRC circuits you have a inductor, a capacitor, and a resistor in the same circuit, and the currents is changing, is charging the capacitor, is passing through the resistor all the time, so it will create interesting kind of circuits over here. Okay, so that is sort of like a introduction to this chapter. So now we should start to jump into the first topic, which is Faraday's law and Lenz's law. So let me write this down first and see if you have any other questions. So Faraday's law and Lenz's law. Okay, so this is going to be somehow related to this, so we're going to do this part first. Okay, so we will see how this works. Yeah, so the current cause, yes, correct. Well, Q is not changing, right? Q is just a moving charge. Because Q cannot change. We have conservation of charges, right? Charges cannot be created or destroyed, so Q cannot change. Yeah, it can flow from one point to another. Then, so that is the best we can do. Yeah, so it can only flow. So then we are still back to currents. So it's just moving Q. Right? And electron charge is always electron, and it cannot change its value of its own charge. So, okay? Right? So that is our setup. So let's see how this works. So let me begin by telling you about the experiment. So this is a simple experiment that we could do in the lab. In fact, if we were having physical class, you could have done this in our actual lab. Is like this. So how do I know that a changing magnetic field creates an electric field? Well, firstly, let us talk about this experiment first. So I have a coil, right? So this is why we kind of learned solenoid just now. So we have a coil, and then this coil is attached to two terminals of a ammeter. So this ammeter will detect a current. So what happens if I hold the magnet on top of the coil? So according to our experiments, anyone can do this yourself. If you do not move a stationary magnet, it does not induce a current in the coil. So zero current if you don't move, right? So if you just hold the thing there on top, there's no current. But if you start to shake your magnet up and down, you start to see that there's a current being detected. So that is also interesting, right? So this is so that is one hint to tell us that the moving of this thing will cause a changing magnetic field through this coil, and therefore it will start to produce a current here. Okay, and then yeah, so we remember about solenoid, right? Instead of a magnet, we also know that a solenoid will also produce a magnetic field. So if I take a solenoid and I attach this to a power source, the same story happens. If I just hold this still and if I don't move, I will got zero current. But if I shake the solenoid, like turn on the current, if I shake the solenoid, then it will start to have current moving up and down. And also another phenomena is if you just leave the solenoid hit there, right, but I put a switch. So if I open the switch, that means I open the circuit, no current flowing, therefore no current flowing on the second circuit. I close the circuit, I will detect a current jump for a moment and then back to zero, right? So the back to zero part is the important step, because when you have a steady current, it will produce a steady field. Then it is constant current, constant magnetic field, and constant magnetic field will not create a circuit there. Okay, so that is our starting point. So what the conclusions of all this experiment is telling us that the changing magnetic field through this coil will produce a current. Now, having a current means what? Having a current means there is a EMF inside, right? So which is to say that a changing magnetic field produces an EMF. So after doing all these experiments and getting the results and getting the data, Michael Faraday came up with this law of induction. So this is Faraday's law of induction. Okay. So I hope you understand what I'm talking about, rambling the words. If not, I think the equation or the text will explain in another way. So what the conclusion of the experiment is to say that the magnitude. So Faraday's law is focusing on magnitude first. Direction, that's another story. We will settle this later. But the magnitude of the induced EMF in a closed loop is equals to the rate of change of the magnetic flux through the loop. Okay, so yeah, when we have current, right, when there's a current flowing, there must be some voltage source, right, voltage source, and we call it the EMF because there is not really a battery with two terminals, so we don't really say VAB now because there's no battery here. It's just there's some EMF in the whole circuit, so we just say EMF. So the magnitude of the EMF is the rate of change of magnetic flux, and if the coil has many loops, then I times the number of loops. So this is the Faraday's law of induction. Okay, so that is the thing. So this is the this is the magnitudes only. Later we learn Lenz's law to get the direction. Okay, so Lenz's law, that's why we learn Faraday's and Lenz's law. One is giving you the magnitude, the other one tells you the direction. Okay. I think so, yes. No. Oh, capacitance. No. Farad. Actually, I think so. Yeah, I'm actually not sure. So I should look it up later. So yeah, you propose another way to change charge is position settle, but charge changing. If you talk about particles, cannot, because conservation of charges. So charge changing means there must be some charges going out of the system, right? Conservation of charge. It's like like mass. So mass is like charge. It cannot be created or destroyed, right? If your mass of an object is decreasing, that means it is flowing out somewhere. So that is the conservation of mass. And in the same way, that, it works as a conservation of charge. Okay, so let us, so we will settle Lenz's law later, but let us see how to use it just to get an idea by solving this example. So in this example, we have a magnetic field between two poles of an electromagnet that is uniform. So it looks like this. We can treat this as a uniform, but the magnitude is changing with time and is given by this formula. So it's linear in time. So lambda t plus a constant, and the constants are given here. So the area of the loop is also given straight away, 120 cm square. The resistance of the circuit is 50 meters. So find the induced EMF and find the induced current. Okay, so that is the question. So let us see how to solve this. So we are at example 7.1.1. So the magnitude of B is lambda t plus a constant. So lambda and B naught are constants, right? So lambda is given as 0.0 Tesla per second, and then B naught is 0.001 T. The area of the loop is 120 cm square. So if you convert this to SI units, is 0.12 meters square. The resistance of the circuit is 5.0 ohms. Okay, so from here we can easily see what is the flux. What is the flux through the loop? Is just B times A. Am I right? Very simple. So flux through the loop right? So the formula for flux, remember, is supposed to be B dot dA and then integral
but at the end it's just B times A because it's uniform and everything is straightforward. So B times A, so it's just A times this thing, so it's lambda T plus B naught. Okay, and I want to, and oh yeah, for this problem n is equals to 1 because it's just one loop. So what is the EMF induced? So the EMF induced, so this is to solve part A, right? So the EMF is just the rate of change of flux, but n is equals to 1, so it's just times 1, right? And what is the rate of change of this flux? So we have calculated the flux already, so this is just d dt. Yeah, so in this chapter the differentiation is important. Remember your calculus stuff, but we differentiate, right? So we differentiate A lambda T plus B naught. Okay, so we differentiate this with respect to time. So this is a constant, so if I differentiate, the last term will disappear. If I differentiate this, what do I get? I get A lambda. Right, so A lambda are just positive numbers, so I got this. So my EMF is just A lambda, right? If I multiply these two values, I will get 2.40 times 10 to the minus 4 volts. So this is my induced EMF. And then to get the current, we use Ohm's law, right? So V is equals to IR, so the current is just the voltage over the resistance, which we know all the values already. Resistance was 5 ohms, so the current flowing through this is 4.80 times 10 to the minus 5 amps. Okay, so this is a straightforward application. The main point is, for this question, this is still simple one, but it will get complicated later. But at the end of the day, always remember, find a formula for flux. If you are able to find a formula for flux, the EMF is just differentiating this with time. Another important thing, differentiate with time. So anything related to position, it can be 0. This is just differentiate with respect to time. Now, part B is asking an interesting question. If the loop is replaced by insulator, then what happens to the EMF and what happens to the current? It's kind of a pretty straightforward thing. One thing to notice is that my Faraday's law is strictly referring to rate of change of flux. It has nothing to do with the conductor, whether it's a conductor or an insulator. So the value of resistance is independent of Faraday's law. So what I'm trying to say is Faraday's law is independent of resistance. Okay, so just now my resistance is 5 ohms, right? But no matter what, my EMF is still the same, right? So even if my resistance of my wire becomes infinity, right? Insulator means infinity resistance. The EMF is still, because our calculation doesn't care whether what is the resistance of this. So the EMF technically is still 2.40 times 10 to the minus 4 volts. Okay, but the current I is EMF over R. So for insulator, the current is 0. Okay, so it's just to teach us a lesson that, yeah, voltage and current are slightly different things. Not slightly, but actually like totally different things, right? Current is just current flowing. Voltage is EMF, I should say. EMF is the potential difference across a system. So that will have something to do with the electric field itself. The I is just, yeah, whether the charge can flow or not. If it's an insulator, no matter if it's a perfect insulator, if you put a potential difference across an insulated wire, the charges can't flow, right? It's an insulator. So that is what this means. Okay? Any question? So it's the same guy, okay? Interesting. Yeah, I didn't know that. Yes, correct. So the experiment, yes. So the experiment that was done is to tell us that, okay, there is a current, and the main reason there is a current is actually the EMF. So Faraday's law is actually, yeah, focusing on the EMF itself. The EMF is the important thing. So because current still, another reason is current still depends on the resistor. So current depends on two things, and that is why. Okay, so yeah, I guess now let us take a 10 minutes break. How to measure EMF using voltmeter. EMF. So it depends on the experiment, I guess. Yeah, you can call it EMF meter, or you can calculate using Ohm's law. So if you are using a wire and you know the resistance, then you can use Ohm's law to calculate the voltage also. Yeah, I shouldn't waste too much time. Anyway, h bar is just h over 2 pi, right? And then omega is just 2 pi f. So h bar omega is just h over 2 pi f is hf. So these two formulas are the same. And then for harmonic oscillator, I think the formula is h bar omega. This is the frequency of the oscillator, and then is n plus half, I think, and then n is the integer, right? So 0, 1, 2, ... So that is the simple harmonic oscillator. That is also very important in quantum mechanics, and also quantum electrodynamics when we learn how to quantize the theory. So yeah, anyway, let's talk about Lenz's law. So I mean, we should be doing some tutorial. So if we have some remaining time, I will do tutorial later. But I will definitely upload everything for tutorial 5 today. So don't worry about it. Okay. So because I think tutorial 5, most of them are fairly easy questions. Probably the harder ones are in tutorial 6. So we will spend more time doing tutorial 6 later. Okay, so let's get started with Lenz's law. Yeah, so X-rays are just photons of a different frequency. I'm talking about this because we will be covering this in chapter 9. The different types of light: X-ray, radio wave, microwave, infrared, optical light, infrared, UV rays, all what else? Yeah, gamma rays. So these are just a continuous range of frequencies. So depending on what is the value of your frequency, you will get different types of light. But these are just the names that we give to different kinds of lights. Okay, so here we are in doing Lenz's law. So as I was saying, right, Faraday's law tells us how to calculate the magnitude of the EMF, but how to get the direction. This might be slightly tricky. So let me write down the law first. So the law is that the direction of the magnetic induction effect is always to oppose the cause of the effect. Yeah, I kind of forgot to introduce to you the terminology, right? The magnetic induction is where the changing flux creates EMF. So this is what we are doing, Faraday's law and the Lenz law. The Lenz law will tell us how to decide on the direction. Okay, so there's two ways to determine the direction of the magnetic induction. So one is I will call the simple way, and one is to imagine. So there's two methods, right? Method one is kind of like a mathematical official formula. Then you just apply, then you can never go wrong. The second way is just to imagine the loop as some kind of stubborn human, and it's always want to go against what is happening to it. So that is another way to determine the direction. So what do I mean? Well, let me show you. So let me start with just the but let me write this down first. So the oppose, right, means that, okay, the sign of this is just d phi dt. So the Lenz's law is just to give you the sign. But even if I write down what does this equation mean, right, I need to define the direction. Then only I know what is the sign. So anyway, let me write this down first, and we can figure out what does the negative sign mean. So I will show you two methods. So the first method is firstly is this is a magnetic flux, right? And we remember that magnetic flux we derive by integral of B dot dA. And then I have two vectors. So the magnetic field is just given in the situation, then you get the direction there. The area vector also has a direction. So the way to determine the direction is to determine the positive direction of A. Okay, once we get the positive direction of A, and then we get this positive direction, then we can calculate the B, and then we can get the sign of phi. So the sign of the flux, it could be positive or negative, right? You just calculate by the dot product. Because if your magnetic field is opposite to your area vector, then the dot product is going to be negative. As long as greater than 90 degrees, it's negative. If your magnetic field and your area vector is less than 90 degrees angle, it will be a positive flux. So that is the positive flux. And once you get the sign of this, you can also calculate the sign of the time derivative. Okay, so that is also another thing, right? So once you get this, you can get the sign of the time derivative. And finally, once you got this, the sign of the EMF is the opposite sign of the time derivative. Okay, which is why we got the negative sign here. So this is very abstract. What do I mean? So let me draw an example. So let's draw a loop. Right, so let's draw a loop. So let's give a scenario. Right, so let's give a scenario, a concrete scenario. So let me say that, let's put an example. Magnetic field is in the K direction, right? And then my coordinate system is X, Y, Z. Okay, and then the magnitude is increasing. Okay, so increasing. So let's draw a loop. So this loop is in the XY plane. Okay, so this loop is in the XY plane. Right? And then this is in the Z direction. So yeah, no need to do this. Okay, so this loop is in the XY plane. And then I will decide the positive direction of A. So this one is also using the right hand rule again. What do I mean? So if I say that my area vector is this, okay, that means this is the positive direction of my loop, right, using my right hand rule. So this is the positive direction. I'm talking about the loop. I haven't talked about the current yet because this is just the geometrical shape. Right, we haven't talked about the EMF yet. So the EMF, it will, by this law, I can get the direction of EMF. But because just like when we are doing anything mechanics, right? We always say, when we're solving a question, we always say upward positive or downward negative, remember? Right? When we talk about rotational motion, we say clockwise positive or anti-clockwise negative, right? So same story happened here. We say that we define the positive direction to be anti-clockwise when I look down onto it. Okay, so that is my direction, and that is my direction of area vector. Okay, so then if I take this, right, my B vector is pointing here, so my flux is just B dot A, so it's going to be some positive number, so it's just going to be B times the area itself, right? So it is positive. Okay, so it's positive. Then what is the time derivative? So it is increasing, so my time derivative is, well, A is a constant, B is increasing with time, so it's A dB dt. So this is increasing, so it is a positive number. Right, so if this is increasing, then according to my law, my EMF is negative. So let's say my loop is n equals to 1. Right, then it's just negative d phi dt. So it's negative A dB dt. So this is a positive quantity, and I put a negative sign. My conclusion is that the EMF is negative. Okay, so over here we say that the clockwise is positive, right? No, anti-clockwise. Then EMF negative means it should be clockwise. So what is the direction of the EMF? So the direction of EMF is anti-clockwise, so it's going this way. It's going this way, clockwise. Any question? Yes, actually correct. Is the orientation. Yeah, in mathematics, the official terminology is the orientation. So, but it's the same thing like what we did in physics, right? When we do a calculation, we must define right positive or left positive. We do that all the time since mechanics. And even your high school also, right? Down positive or down negative. G is plus G or minus G. Same story happens here. Okay, so using this method, in this example, we go through these steps. So I know that this is like very mathematical calculus kind of stuff. So that's why I will show you a second method. So the first method is like, yes, exactly in calculus 2. This is the orientation of the loop, so of A. Okay, but second method is a more relatable method. Is that just to imagine that the according to Lenz law is always opposing the cause. So this is what I call method 2. We just imagine that the loop is very stubborn or rebellious. Always against everything. I think if you just imagine the loop is very stubborn, you can easily get the direction very easily, right? So yeah, so let's take an example again. So let's take this example again. And then I got the magnetic field increasing. Okay, so what I'm having here is, yeah, I have an increasing flux. So if this is increasing, it will cause this to increase, right? Increasing flux. Yes, kind of. Yeah, kind of. So, but we do not need to relate this to, we will relate this to forces and energy later, but for now, yeah, for now, let's just like make it easy and just imagine that the loop is very stubborn, right? So if the loop is very stubborn, right, he will don't like this to increase, right? A stubborn loop or rebellious will don't like this to happen. So if you don't like this to happen, then it will make a current it will make a EM, oh, well, let's talk about EMF first, such that the resulting current opposes okay, so it will opposes what is happening, right? And okay, fine, what's happening? What's happening here is the flux is increasing, so phi b increasing. So if I want to oppose this, I want to make an EMF such that the resulting current to oppose this. So how do I make EMF? Well, the flux is opposing, so the EMF will make the loop, the stubborn and rebellious loop, it will make a current to fight against this. So if this is increasing this way, so what the current will want to do is, I will want to create a current such that it will create its own magnetic field to fight against what is happening. So if this is increasing, then what you do is you go the other way. Then how do you go this other way? Well, I want to have a current that is going in this direction, so this is a clockwise current, right? So same thing that is happening here. Clockwise current. Okay, so that is the main way to determine the direction, right? So if the B is increasing, then what you do is, yeah, you fight against it. Okay, then now you can try to think, okay, the counter example, if B is decreasing, then what do you do? Yeah, kind of, yes. So why is this energy conservation, as Zuri was saying, right? Because if okay, so let's say this is not true. If this is not true, that means, what if the opposite thing happens? So let's prove this by contradiction. If the opposite direction EMF is generated, then the opposite direction EMF generated, it will create even more magnetic field. Okay, so magnetic field increasing, it will create even more magnetic field. So that means the magnetic field, like extra bonus magnetic field, come out of nowhere. So that is violating conservation of energy, because later we will also learn, because we haven't learned this yet, magnetic field carries energy as well, right? Same thing like electric field carries energy. We learned that in capacitors. Magnetic field also carries energy. So if I have an increasing magnetic field and then I have an EMF that generates even more bonus electric field out of nowhere, that means magnetic field keep on increasing for no reason. That is a violation of conservation of energy. So then that means this is not true. So the other case must be the one that is happening, right? So it will oppose the change, so that the energy flow will be conserved. Okay, so let us see, right? It depends on the dB dt. So let us imagine, so let us think of another scenario. So this time let me draw it in this way. So let me draw it in this way. X, Y. So my Z is this direction. So let us say that my B is B in the K direction, but this time this is decreasing. So that my dB dt is a negative term. Okay, and what happens in my what happens to my loop? Okay, so my loop is in the xy plane, but my magnetic field is coming this way, but it's decreasing. Right, so let's say it's so I got a flux. Am I right? So my flux is yeah. So let's do method 1 first. Method 1 is to decide the direction of the current. Right. So let me use the right hand rule. So I will define right hand rule. Let anti-clockwise be positive. Right, so this is my positive direction. Okay, that means my area vector is also along the k-axis, right? So if I take a clockwise, then my area vector is along the z-axis as well. So A is this, and then B is this. So therefore my flux is just B dot A. So I just dot these two vectors is just AB, right? And then I look at the time derivative. So if I take the time derivative, what I have here, area is a constant, right? Assuming the circle is constant, we will solve an example where area is not a constant. So that one is later, but for now, this is constant. Then what we have here is dB dt. And then this time it is decreasing, so this is a negative number. Then my EMF is using Lenz's law combined with Faraday's law. So again, let us take n equals to 1. So that means I'm differentiating this, so I got negative A dB dt. So this is a negative term, this is another negative term, so we have found that my EMF is positive. So we have defined positive to be anti-clockwise, so it is this direction. So I will cause a EMF current that is pointing this way. Okay, so that is how we get the direction of the EMF. So that is method 1, right? So what it was, how? So if you don't like method 1, okay, if it's too mathematical or too abstract or too confusing, then let's go to method 2. Loop is very stubborn. Okay, so loop is very stubborn. It will oppose the change, right? Opposing the change. What's happening? So we look at what's happening. So what is happening here is the flux is AB, but B is decreasing, so flux is decreasing. So when the flux is decreasing, then how do you fight against a decreasing flux? So to fight against the decreasing flux, I will want to make a current that will fight the decrease. So the magnetic field is getting less and less. The stubborn loop, no, I want to keep my magnetic field there. So I want to keep my magnetic field there. He will make a EMF so that the current will contribute magnetic field. So that is why you make a current here, and then if you use the right hand rule, the magnetic field will supplement to top up the magnetic field. So so that means I will make a EMF so such that the current will contribute, right, or top up the flux. Okay, so it's always opposing the change. So always opposing the change. So that means you will make a current that will contribute the magnetic field. So that is why the current is this way. Because if the current is the other way, it will make the decreasing even worse. That means, yeah, it will make the decreasing even worse. So that is not what the current will want to do, because the loop is very stubborn. It's always fighting against what is happening. So if flux is decreasing, you make an EMF to increase the flux. Just now in the previous example, when the flux is increasing, you make an EMF that will decrease the flux. It's always opposite to what is happening to it, right? Just imagine the loop is very stubborn, right? So most of the time, this is my favorite method to get the direction, because yeah, it's not so mathematical. You just think, what would a stubborn person do? And we can easily get the answer. Okay, so yeah, at least I showed you two different methods, so you can use whatever method you want. If you use it consistently, you should be able to get the correct direction. Okay, so yeah, does anyone have any questions? Okay. Yeah, so Jiacheng already helped me explain. Let's just say. What do you mean? You mean in the exam, is it? So obviously, if you are taking the exam with me and you say stubborn, you know what I'm talking about, right? But if you take the exam with someone else and then you say stubborn, and then like, huh, what are you talking about? Then you get 0 marks. Because the stubborn is my own personal term. So if you use this language with other people, then they'll look at you like crazy. So yeah, but if you're taking the exam here, then fine. The important point is to get the correct direction. What's the next example? Okay, this example is still fairly simple. So I have a 500 loop, so n equals to 500 now. So this is in example 7.1.2. N is equals to 500, and then the radius is 4 cm. So it's a circle, so I can get the area very easily. Placed between the poles of a large electromagnet. So basically it looks like this situation. Magnetic field is uniform, angle is 60 degrees, and the magnitude decreases at this rate. So what is the magnitude and direction of the induced EMF? So yeah, according to this question, it is decreasing at the rate of 0.2 Tesla per second. So that will give me information about dB dt, right? So dB dt, negative because it's decreasing, right? The dB dt is decreasing over time, so the differentiation will be a negative term, right? A decreasing function, and it is decreasing, so it's negative of this number, right? So that's why it's decreasing. Okay, so in this question, the magnetic field is uniform. So let's get the flux. So if this is uniform, then the flux is just integral B dot dA is just B dot A, right? So it's just BA cos phi. Okay, and then oh yeah, so I kind of skip straight to this picture. So let me define my area vector to be this way, and then my magnetic field is this way. So the angle is like this, right? So my direction of my loop is this, right? So it's like it's very hard to describe because it's now facing to us now. So it's coming towards us on top and going away of this. So direction of loop. On top, below, right? So it's like on top, below. It's in 3 dimensions. So that's why you got B dot dA, BA cos phi, right? So now we can find the derivative. with respect to time. So I'm just differentiating d dt BA cos phi. So phi is a constant because according for this question, the loop is just fixed in this position all the time. Area is fixed also, only the magnetic field is changing. So therefore, you only need to do this. And we know this number, right? So we know this number. And therefore, the EMF is just negative of A cos phi dB dt. So it's the area is just the pi r square. So it's 0. It's 4 times 10 to the minus 2 square. And then the angle, the diagram is already given in the question. The angle is 30 degrees. And then this is 0.200. So if you calculate everything, you should get, there's an n. So there's a 500. And then finally, you get a positive 0.435 volts. So I got a positive EMF, that means it is this direction, right? So it's coming out on top and then going inside. Area vector negative just means that the area vector is here. Yeah. So you can also define this to be my negative area vector. So A2 is, yeah. So that means this is just defining the opposite direction. So in this direction, then my current is going, my direction is in this way and then out this way. So it's the other direction. How to draw 3D this way and this way. So the previous direction was coming out and then coming in. Correct. The actual area is a scalar. The area vector is the perpendicular vector that's sticking out of the area. Yeah. So actually don't be confused by all this convention and stuff. Even if we have convention, right, actually it's the same thing that we did even in your high school. If you solve a mechanics question, you need to say upward is positive or downward is positive, right? We have done this before in the mechanics. Even not mechanics, in your high school, when you solve an object falling from height A to height B, you use Newton's law, and then you need to say down, whether it's down is positive or down is negative, right? And then if you get a negative answer, that means it's the other way, you know? So it's the same story here, just that it's now clockwise or anti-clockwise. And if you did mechanics with me, we did rotation also. Sometimes we say anti-clockwise rotation is positive or clockwise rotation is positive, and so on and so forth. It's the same story here, right? But again, this is method 1. So if it's too mathematical and too weird, then just imagine the loop is very stubborn. So the loop is very stubborn. The flux is decreasing. So if the flux is decreasing, then you just think, okay, what's happening? The flux is decreasing. So what's the flux? So the flux is the magnetic field is passing through here, right? So the flux is decreasing. If it's decreasing, what do you make? Right? You want to fight against a decreasing flux. So you want to top up, right? So you want to top up. So in order to top up, I want to make this current so that I want to create a magnetic field to supplement this, right? So the current it supports not against B, so it's this way. Vector times scalar, yes. How do you know the direction of the area vector? So okay, I kind of do we have much time? Okay, so let's do it. Yeah, I kind of like skip through a lot of details. If you want to know how to get a let's go through the concept of area vector again, because I think this is confusing a lot of people, right? And right now, as we go further and further, this is getting more and more important. Okay, so let's take a coordinate system. Let's take x, y, and then y. Then this will be z. Okay, let's take a coordinate system, and then let's take an area, some area over here. Okay, so this is an area, right? And of course, like Zuri said, yes, you're right. Area is just some area, so it's a scalar number. It shouldn't have a direction. But what is the area vector? So for area vector, I need to include a direction that is perpendicular to the area itself. So there's two choices, right? Because there's should this be my direction of the area vector, or actually this is also still perpendicular to the area, right? So in both cases, these are perpendicular, right? So which direction to choose? Okay, so what we do is we choose the decide by choosing the direction of the loop around the area. Okay, and what do I mean by this is, okay, so let's say I have this area. I choose the loop. So let's say I choose let's choose anti-clockwise. So if I choose this, that means my direction will be this way. Correct? If my direction correct, then my area vector will be this way. Okay, so maybe this is a bit to make it even more easy to imagine, let's draw a square area. So let's draw a square area. I think it should be better having a square area. So x, y, z, and then let's take the area A. A lah. So the area, the magnitude of area itself is just A square. Okay. So if I choose and if I choose this, right? So so if I choose this direction to be positive, okay, then therefore my area vector is going to be this way. So if I choose x, y, if I choose this one, right, clockwise, anti-clockwise positive, then the area vector is just A square in the k direction. Is this clearer now? It's not the projection, it's just, no, because area vector is just, okay, the magnitude is the area, and then the direction is this thing here. Okay, so not really projection, because we're not projecting anything here. Okay, so then let us, just to finish everything off and make it absolutely clear, let us choose the other choice. Okay, so if I choose the other choice, let's take a square shape again. Right, A. So the area is still A square. This is my z-axis, but now I choose clockwise positive. So clockwise positive means this way, right? So this way, this way, this way, this way. So if I do clockwise positive, if I use my right hand rule, my area vector is now pointing down. So then my area vector is negative a squared in the k direction. So it's a choice. But again, let me emphasize, this is method 1. If you don't like method 1, use method 2. The loop is very stubborn. Yeah, then you don't need to worry yourself about, don't need to confuse and be scared about this. But ultimately, method 1 is the official mathematical definition, and official mathematical definition will be important, more and more important as we go to later years. So even if you focus on method 2 for now, is fine, but at least just keep these notes. Maybe you might look at this again in the future. Right? Okay? Yeah. So okay, let me emphasize, it's not effective area. You get an area and then you get a direction, because vector is two things, right? Magnitude and direction. Magnitude is that area itself. Direction, you figure it out using this way, right? It's not really an effective area. The flux, in that sense, projection is what happens when you do a dot product. So this one is like kind of the effective area of the magnetic field across the A, but it's just an interpretation. So I think, I better not add more confusing things. I better not add more confusion, but that's the general idea of it. Okay. I kind of spent too much time talking about this, so it's already 10:50. No time to do tutorial, and in fact we are totally out of time, right? Yeah, so can treat like effective area. Well, I mean, it's an area, right? So there's you can call it an effective area, but it's still an area. So I don't know. I mean, depends on what you mean by effective area. Area is area, a square. The area is a square. Do you agree? Right? The area of the square is a times a, length times width. So I guess I will upload the tutorial solutions, and if you have any questions, just let me know. And we definitely ran out of time, so let me stop the recording.